now that we know a bit about the Arrhenius concept, and the main takeaway from the Arrhenius concept was that acids produce H plus and bases produce OH minus. We need to get a quantitative measure of the strength of acid or base. And the way we do that, the way that's most common to do that sort of quantitativeness, to bring that quantitativeness to table, is called the pH. P in small, H in capital, and this it stands for the German word potens. I'm sure I'm mispronouncing that, but anyway, pH really gives you the strength of an acid, And the way the pH is defined, and it was defined by a great scientist called Sorensen. And what Sorensen defined the pH is the log to the base 10 of 1 over the molarity of H plus ions. And let me come to all of those points. So the log of 10, if you're not familiar with what logs are, let's do a quick brief introduction to logs as well. So you know about exponents. So 10 to the power of 2 is equal to 100. So what you can do, you can rearrange this equation into writing that log of 10 to 100 is equal to 2. And what the log means is what power should you raise to this number, to 10, to get the number 100, and the answer is 2. And you can do that for all numbers. So let's move on to the other parts of this expression. 1 over is just a reciprocal, and the H plus molarity is the concentration of H plus ions, and it's in molarity. It's the molarity concentration. So what you can do now is you can go on and you can take any sort of system in which you have H plus ions and figure out its pH. So let's try I don't know, let's take a 1 molar HCl solution. And if you don't know how to calculate molarity, go on and see a video from Dina Academy. And if you have the molarity, if you have 1 molars of molarity, what you can do is you can plug that into the equation. So log 10 of 1 over 1, and that's just 1. You don't need to write molars if you already have it in the units. You don't need to write m everywhere. So log 10 of 1, and so this basically asks to what power you would raise 10 to get 1, and the answer is 0. So the pH of a 1 molar HCl solution is 0. But notice the granularity behind this. I have skipped over some steps. The denominator was asking for H plus concentration and not the concentration of the acid. So what did I do here? So the trick here is that we know that HCl is a strong acid, and so we can assume that it completely dissociates into H plus ions. So any X number of HCl molecules would give you the same X number of H plus ions and the same X number of Cl minus ions, and thus you can take it for granted that for a relatively strong acid such as HCl, 1 molar of HCl would also give you 1 molar of H plus. And that's where the trick comes in. Let's say you had a acetic acid, you had the vinegar that we used, and so let's say you had 0.2 molars, or let's just take 1 molar. Let's just make it simple. 1 molar CH3 CaCOOH And this is the formula for acetic acid, the household vinegar that we use. Now this CH3COOH is not a completely dissociating acid. It's not a strong acid. So you only get some parts. You only get some parts of this acid to convert into H+. So if you started with, let's say, 1 here, you might get X here, and that X would be lesser than 1 because you still aren't completely dissociating. So to study these types of acids and also these types of bases, we need to further explore in the acid-base theory, and that we will do in the next few videos. But for now, just consider the fact that for a given concentration of a strong acid, you can take that to be equal to the concentration of the H+ ions as well. But for the weaker ones, you can't do that. A quick bit of ideas. So usually you will see the pH varying in the range from 0 to 14, but this is not a true equation. So why not? So let's say you had 10 molars HCl. In that case, you're writing log of 10, the pH, you are finding the pH, log of 1/10 to the base 10. And now the question that I'm asking is that to what power I would raise 10 to get 1/10, and the answer is -1. So the pH of this solution is in fact -1. It's lesser than 0. So don't fool yourselves, don't trick yourselves in believing that the pH only varies from 0 to 14. It can be any number. It can be any number, though there are practical bounds. You can calculate practical bounds for each case. The pH can vary technically anywhere. It's just a number at the end of the day. You can also have a pH greater than 14. If you had something like 10 to the power -15 molars of HCl, and since you can just assume that the H+ concentration and the HCl concentration are equal, you can do that. You can write the pH expression, and you would arrive at log 10 of 10 to the power 15. So the answer in this case is 15. To what power you must raise 10 to get 10 to the power 15? You already have the answer. It's 15, and it's greater than 14. So the pH can be any number, and the way you calculate it is you take the inverse. You take 1 over the H+ ion. H+ ion concentration. This is in moles per liter. And you do this operation, and then whatever answer you get, you do the log of it. You do the log to the base 10 of it. The log is available on most calculators, on most scientific calculators that you use. Otherwise, the values would be given in a log table that's presented in some sorts of exams. So, and that's not it. I almost forgot to introduce the pOH. And the pOH is kind of the analog of H+, and it's just log to the base 10 of 1 over OH minus, and just the same calculations that you did for pH, you will just do the same for pOH. Again, OH minus is in molars, so nothing technically changes. So hopefully this has been a quick intro to how to calculate pH and the common misconceptions that you might have. The most prevalent misconception being that the pH has a bound for going from 0 to 14, and you know that it's just a number, so that simply isn't true. And now in the next couple of videos, we'll develop the concept of pH as a not just as a qualitative measure, but quantitative measure, but also as a tool for qualitatively understanding what goes on in acid-base equilibria. See you in the next video.